Namaskar, my dear friends. Let us talk about IPM system design. So what we'll do is we'll talk about a complete design for intelligent power modules from Mitsubishi Electric. Okay. So as you can see, we have various SLIMDIP packages. So we will be talking about one of the part which is SLIMDIP-S. And we will talk about complete, like IPM system design, its control by microcontroller, and how to, like design complete circuit. And the part number that we are taking from is Mitsubishi Electric. Okay, so as you can see, the part description is basically the capability is 600 volt and the current rating is 5 ampere, and we have various other parameters. Basically this particular SlimDip package goes up to 5 ampere to 30 amperes with different versions like S, M, L, W, X. Okay, our aim is to start with S package. Okay, so SlimDip S we are going to talk about, and we will talk about complete circuit around this. All right. So already we have already seen this particular SlimDip package, what are the different features, and like it has a lot of protection like under voltage protection, short circuit protection, over voltage protection, over temperature protection. Okay, then we also have like fault signaling, like it will give you a fault signal output. Similar to that, we have also seen earlier like what are the different applications that it can be used for. So basically the SlimDip S package can be used in air conditioner, cloth washer, refrigerators, dishwasher, fan, pump. Okay, and specification if you talk about, so this is the specification that we have already seen. Now we'll start with our circuit design. All right, so as you can see, this is the particular package that we are talking about, SlimDip S package, and the symbol has been designed in such a fashion that you can see we have VUFB, VUFS. Okay, so this is positive, this is negative, and this is designed with this particular circuit. Okay, so you can see we have capacitor, and then this is filter capacitor kind of thing, and we have a clamping diode as well. These two are test points. So all these are like TP29, 30, 31, 32, all these kinds wherever you see in the circuit, those are all test points. Coming back to the other part, this is being driven by high side and low side PWM controllers. Okay, so we have H in U and L in U. So basically it will be controlled by PWM 1A and PWM 1B. Similar to that, other pairs will be like 2A, 2B, 3A, 3B. Understood? So this is how total 6 pairs of PWM signal will be coming from the microcontroller. All right. Next part is we have DC link capacitor. So this is my DC link capacitor, and this is the high voltage that is going to come up here. So if you want, you can put it here, like around 300 volt, or 200 to 400 volt you can feed it. Okay, and this is our motor connection. So motor driver is here, like you can see U, V, W phases. So all these three phases can be connected to this particular terminal block that has been given. Similar to that, we have these three current sense resistor, 30 milliohms is given for U phase, V phase and W phase. Okay, so this is how it is given. The best part of other things that we'll see first, like we have power supply, so VP1 and VN1. Okay, so this is power supplied by 15 volt. Okay, with these many capacitors, and this is a clamping diode that is given. Similar to that, we have fault output, so FO is there, that has been pulled up and then it is sent to your microcontroller input. All right, similar to that, we have VOT sense, like over temperature sense. So over temperature sense is also pulled down and then send it to your ADC pin. All right. This is actually IO pin, FO pin. Now this C in is nothing but your short circuit protection. So short circuit protection is coming from this this particular current sensing resistors. Okay, so it is going here, and then it is getting, like going through the comparator. So this is a very unique comparator that has been used, okay, RT8H052C. If you want, you can have various other parts as well. So for, like better understanding, you can reach out to us and we will give you exact other application, other, like implementation process as well. So these three comparators are going into this particular comparator circuit. So all these three comparators are inbuilt here, and then this is my short circuit protection output that will go to this particular VC in. Okay, and this is a, like a transistor based driver. So this is P type transistor based driver. Okay, and then this is going to come up here C in, and then this C in is going to get connected. So understood the process. This current sense resistor for short circuit protection, this is going to this comparator. This comparator output will be coming here, and this is going to be driven C in and then getting connected at this place. So this is how it will be short circuit protected. The voltage reference for this particular circuit has been designed through this 15 volt itself, and the value is 0.526. Okay, so 31.6 kilo ohm and 1.15 kilo ohm you can utilize. If you want, you can use other values as well, but make sure the V reference value is this much. Moving to the next part of the circuit, we have current sensing. Okay, so what happens is I didn't tell you here, this particular NU, NV, NW, these three lines can be taken NU, NV, NW. So these three names are going to go through the amplifier, and there the current flowing through the resistors can also be monitored. Okay, so what is happening? This NU, NV, NW, that is going to go ahead with this particular amplifier of gain 10. Okay, you can see R2 by R1, that is around gain 10. Okay, and a voltage reference has been generated by this amplifier and amplified, like it is kind of buffer. So this voltage reference is 2.5 volts. So this voltage reference 2.5 volt is connected of each of the positive terminal of the amplifiers, and then this is going to our current sensor NU, and like current sense U, current sense V, current sense W. Alright, so hope you have now a good understanding of how to send your current sense amplifier to your ADCs. Alright, so this is my voltage reference generation. How voltage reference is generated? Simple, very simple. Like I don't want to use a voltage reference IC for that, because like that may be little costly. However, this VCC is my 5 volt. So 5 volt divided by 5.1, 5.1 K is there. So this Vx will be 2.5 volt, and then it has been buffered, and then this my Vref C will become 2.5 volt, same, right? Moving to the next part, we have implemented, like before this scan, what we'll do is we'll go to the microcontroller. So this is the microcontroller that we have used, TMS320F280037 48 pin package. If you want, you can go ahead and use, like a 100 pin package as well. Okay. So F280037 SPT, this is having another version of like automotive microcontroller as well. So if you want, you can do that. Now what is happening is, this particular microcontroller is giving you 2 DAC output also for various other purpose. So if you want, you can use that as well. And this V reference DAC you can utilize 2.2 microfarad. Okay. Then this is my ADC measurement of various power supplies, like this is 15 volt measurement, this is 3.3 volt measurement, this is 5 volt measurement. On board, one more temperature sensor I have used, which is temp sense A. Okay, and then this is coming from the IPM VOT sense. Okay, so VOT sense is coming from your IPM that we talked about, temperature sensor. Okay, then we have current sensor, current sense U, current sense V, current sense W, and then one potentiometer I have put separately in my own board for various other like testing purpose, so that you can have. Similar to that, the 6 PWM that has been generated is PWM 1A, 1B, 2A, 2B, 3A, 3B, and 4 is actually generated just for like option purpose. Then we have two deep switches for various other application. We have a push button, one push button is there, and two LEDs are also there. Okay, so LED 0 is connected here, but one more is there. Then the fault signaling that was there from IPM, that has been connected here, and we have like communication technique. So I2C communication is there and CAN communication is there. So CAN RxTX and I2C SDA SCL is there. So hope you have now a complete pin description and its utilization. Now this particular microcontroller is going to support external board also. So if you do not want to use the internal IPM, then what you can do is a connector is given, 10 pin connector, which is comprising of the PWM signal plus output, this temperature sensor output and fault signaling output. Got it? Then coming back to the our decoupling capacitors, so VDD-A, you can see VDD-A 2.2 microfarad and 0.1 microfarad is there. Then VDD MCU, that is actually generated from internal, so that just need a decoupling capacitor. Then we will be having VDD-IO. VDD-IO is actually being generated from VDD, which is 3.3 volt. All right, so this VDD-IO is going to get connected here, and this is how it is done. Coming back to the reset, so this reset pin is there, that is XRSN, and this is JTAG connection. So JTAG connection for programming purpose. Now for this system I need power supply. So power supply, we have let's say first this discrete signal. So we have an audio buzzer that is being driven by this particular PWM. Okay, so this one you can put it 0 ohm. Okay, then as I told you about potentiometers, one potentiometer is connected here. Then as I was talking about like I2C interface for EEPROM, so this I2C interface EEPROM will be having some data for the motor like driver, so some data log can be put here. Then we have onboard temperature sensor that we have put it here. And talking about the voltage measurement, so 5 volt is being measured by this particular voltage divider. After buffering and filtering, it is going to ADC VCC. Similar to that, 3.3 volt is being monitored and sent to ADC VDD. Then this V in A is actually 15 volt input, which is going to be measured like this and going to go to your ADC V in A. Okay. Then we have two LEDs, LED 0, LED 1. This is pin is not available, so I have just put a test point here. Okay. Then we have two deep switches, one is like 0 and 1, so only one is connected to the pin, other one is left out, that is not a problem. And we have one user push button for various control that you want to have. As I was talking to you about like various power supply design, so we'll talk about power supplies here. So as you can see, this is the power supply connector. So you can connect it like 15 volt directly here with a huge safety. It is going to V in A here. Okay, or otherwise if you have a adapter jack, you can connect like a power adapter directly, and through this it will come V in A. So you connect a 15 volt power supply here, so that directly 15 volt you get it. Then this 15 volt is going to get converted by this switching regulator to 5 volt 2 ampere, and this 5 volt 2 ampere is going to get converted from this VCC to 3.3 volt. And this 3.3 volt is going to renamed as VDD through a ferrite bead. Okay, for DAC reference, we have used one DAC reference voltage, like voltage reference IC, that is going to generate 3 volt. Okay, so it is going to generate 3 volt reference for that. And as well as we have various power supply indicators. So for 5 volt red LED is used, and for 3.3 volt orange LED is used. So if it is glowing, it means you will understand that okay, 5 volt is available on the board and 3.3 volt is also available on the board. As soon as it goes down, it means this particular IC is faulty condition, and this is how 5 volt will not be glowing. Okay. Good, let us talk about the interfacing that we have done. So this is my CAN transceiver IC. Okay, so what has happened is this CAN signal is going to come through this particular voltage translator. and voltage level translator is going to give you TXD, RXD, that is getting connected to this transceiver inputs. Okay, so this transceiver is going to convert it to can high, can low with proper, resistor termination of 60.4 ohm, 60.4 ohm, and then we have proper filtering capacitor and proper ESD protection as well. So this is my ESD protection, and then this is going to get connected to my connector. So this is how CAN transceiver is working. Another part is, since my IPM will be taking a signal level of 5 volt, so we have converted from 3.3 volt to 5 volt. Okay. So this is 3.3 volt and this is 5 volt. So you can see we have PWM 1A, 1B and 2A, 2B. So that is going to get converted as input to output. So this particular IC can be used to have a voltage translator or voltage level shift. So this is my controller side, that is microcontroller pin, and this is my IPM side, that is going to go to your H in U, L in U, H in V, L in V. Okay. Similar to that, one more pair is remaining, which is 3A, 3B, that is going to get converted by this voltage translator. So in this voltage translator, what I have used is 3 input lines are there and 1 output line is there. It means 2 lines is being used for PWM purpose and going to go to IPM side, and from IPM side my faulty signal was there, which is going to come as this input, and output will be going to get converted to 3.3 volt and go to microcontroller. So this is how voltage level shifting is also completed. So hope you have a proper understanding of complete circuit that we have designed for this particular IPM that is there in our system. Okay, so if you do have any questions or any understanding that is needed for this particular IPM circuit design, or anything else that you want to put it here, how to start with current sense transistor, current sense resistors. There are other application as well, like how to how to manage this particular current sense resistor with only single resistor. Okay, so that is also possible, so that we can talk about later on. However, good, so you have now a good understanding of how we can design circuit for intelligent power modules using SLIMDIP-S, and we'll come up with other parts as well, like SLIMDIP-X will come up with having higher power range or higher capabilities. However, to start with, I have given you a circuit for SLIMDIP-S right now. And you can have this particular circuit as a reference, and you can start designing your own circuits and control by yourself. And we have already talked about this particular C2000 series real-time microcontroller, which is very popular, and this is the one which we have used already. Okay, so if you want, you can utilize other microcontroller as well, like 39 series or 37 series of 64 pin, 100 pin, 48 pin, 100 pin, anything is fine. Alright guys, so if you do have any questions or any understanding that is needed externally, you can put down your questions in the comment box and we shall be able to give you answers as soon as possible. Thank you.